Hi everyone, my name is N. Chandrasekhar. Today I am going to give a lecture on B.TECH Unit 3. Topic is transformers. Today we will discuss about these topics, that means transformer, what is a transformer and the working principle of a transformer, purpose of transformer, after that construction and ideal transformer, after that EMF equation derivation along with some examples, and voltage transformation ratio of transformer, and on no load and loaded conditions of a transformer, equivalent circuit, open circuit test, short circuit test, efficiency. These are the topics today we are going to discuss. This is a basic simple diagram of a transformer which indicates core, windings, supply and load. So here I am indicating the supply, which is AC supply, and after that here the current direction, that is indicating with the I1 because it is a primary side. Basically the transformer is having one primary winding and one secondary winding. Where you are giving supply, it is called as primary winding, and where you are taking load, that is called as secondary winding. So here I am indicating the flux direction throughout the core. So here this is the load. So in this transformer basic diagram, here it is indicating with V1, where you are giving supply voltage, that is taking as V1, and after that here E1 and here E2, and this is V2. So if you observe this, V1 and V2 are in same phase and E1 and E2 are in same phase, because we are having right hand thumb rule. That means if you hold the conductor like this, your thumb indicates the current direction and the remaining fingers indicates the magnetic field direction according to your right hand thumb rule. But according to the transformer concept, the right hand thumb rule is applicable to solenoid. What happens is the remaining fingers indicates the current direction and the thumb indicates the magnetic field direction. That is the reason the V1 and E1 are in opposite phase. That is one major important point regarding the basic transformer. So here the V1 itself is called as primary voltage, which is at supply voltage, and E1 is primary induced EMF and E2 is secondary induced EMF and V2 is the voltage across the load. So here these dotted lines indicating the flux or field lines, magnetic field, because the transformer working principle is based on the Faraday's laws of electromagnetic induction. So instead of taking primary and secondary side windings with electrical connections, we are connecting those windings with the magnetic connection. So instead of taking electrical contact, there is a magnetic contact. So this transformer is electrically isolated and magnetically connected. So here the supply must be AC supply, alternating current, because the DC supply is not suitable for a transformer because it is not at all preferable. So here we are giving AC supply to the transformer and we are taking AC supply at the load side. This is one and only machine which transforms electrical power to electrical power, electrical energy to electrical energy. Here you are not changing the energy form, because when compared to other machines, all other machines are converting the one type of energy to another type of energy, but in the transformer you are not converting, just you are transforming the electrical power from one circuit to another circuit without change in frequency. That is the important point. You are not changing the frequency, just you are changing the voltage levels or current levels. So here the transformer is having number of turns. Here it is N1 and here it is N2. So what is the necessity of the transformer? Here the necessity of the transformer is to step up or step down the voltage according to our requirements. What are our requirements? So in the transmission lines, there are I square R losses. To reduce I square R losses, you have to reduce either current or resistance. So here the resistance is equal to rho L by A, resistivity, length and area. So here the resistance is directly proportional to L and the resistance is inversely proportional to cross-sectional area. So either you are decreasing the length or increasing the area, then only you will reduce the resistance value. That is the point. So here you are not in a position to reduce the resistance because you cannot reduce the load point and supply point of distance. The distance between load point and supply point. So the length is not decreasing, then R is not in a position to reduce. So there is only one choice for us, that is to reduce the current value. In what way you are reducing the current value? So here P is equal to V into I into cos phi. This is our formula for AC power. So here you are in a position to change the voltage and current values. So here the current value is reducing by increasing the voltage value. Here I am indicating N1 turns and N2 turns. N1 turns on primary side, N2 turns on secondary side. So one important point is EMF per turn. EMF per turn on either side is same in a transformer. Some of the students get confusing that suppose if 110 volts by 220 volts transformer is there, if suppose EMF per turn on primary side is 10 volts, what is the EMF per turn on secondary side? Suddenly the students are getting that answer as 20 volts. It is wrong because we are concentrating on EMF per turn. Whenever the EMF per turn on either side of the transformer is same, then only you will design a transformer, whether it is a step-up transformer or step-down transformer according to your requirements. If you are increasing the number of turns, there is an increase in voltage. If you are decreasing the number of turns, there is a decrease in voltage. That is the major point of transformer construction according to the required value of output voltage level. So in the transmission lines, when you are decreasing the value of current, then automatically there is a decrease in value of transmission losses. So in that manner, we are increasing the voltage level of a transformer from the generating station 11 kV to 132 kV or 220 kV according to your requirement. So when you are increasing the value from 11 kV to 132 kV, the according change of current will also appear at the transformer secondary side. If you are increasing the voltage level from this point to this point, automatically there is a decrease in current from this point to this point. That is the reason a voltage step-up transformer is also called as a current step-down transformer. A voltage step-down transformer is also called as a current step-up transformer. This is the important point related to transmission lines. And so in this transformer, V1 is the supply voltage where you are giving AC supply with a particular frequency, according to our Indian frequency, we are having 50 Hz of frequency. And here we are having I1 current which is flowing through the primary winding, and here the I2 current which is flowing to the secondary winding. So here the load and the voltage across the load V2. So if you are taking a simple phasor diagram, if this is V1, automatically this is E1. So if it is a supply voltage, it is a induced EMF. So here given voltage and induced EMF, and this phasor will indicate the current value. So it will be discussed in the part of ideal transformer concept. So in what way the transformer is working, even though you are not connecting electrically. So here there is a magnetical connection based on the core material. So this core material is laminated core. Why? Because to reduce the eddy current losses. To reduce eddy current losses, we are laminating the core. So what is the laminations? So lamination meaning is, instead of taking one solid core, you are taking layers of that core which is separated by a insulating material. Then automatically there is a utilization area point is there. Then the laminated core will gives you less eddy current losses when compared to a solid core material. So according to the constructional details, so here whenever you are closing the circuit on the secondary side, then only the current is flowing through that secondary winding. So there are so many cases like on no load conditions and loaded conditions, at different loaded conditions, ideal transformer like this. This is a ideal transformer. What is an ideal transformer? Actually, any machine, any device is having some losses. That means any machine is having different stages. At every stage there is an input and there is an output. How much amount of output you are getting for a given input, that is a important point. So here the supply voltage is given to a transformer and the load is getting the secondary side voltage with a good efficiency, because in the machine's topic, you compare to all other machines, the transformer is most efficient machine because it is a static device. Whenever there is a rotational parts, automatically there are rotational losses. So here in the transformer, it is a static device. That is the reason it is getting more efficiency. So here the ideal transformer is just for our reference only. It is not at all possible practically to take an ideal transformer. No machine, no man are 100% efficient. So every machine is having its own losses. In the same manner, transformer also having their own losses. So this ideal transformer phasor diagram is just for our reference only. What happens if 100% of output you are getting from the input? That is the reason we are discussing about that ideal transformer. What happens to the ideal transformer? If you are giving supply, 100% of output you are getting at the load side. In any machine, what is EMF induced or EMF generated? For that, we are deriving EMF equation of a transformer. So here you have to consider one sinusoidal waveform. If you consider this sinusoidal waveform, here this is origin point and this is one complete cycle which is shown in the diagram. So in this diagram, the complete cycle will take a time of T, capital T. So the time period is capital T, which is also indicating with 1 by F. 1 by F. T is equal to 1 by F. The number of cycles per second is defined as frequency. The number of cycles per second means, suppose in India we are having 50 Hz. That means 50 cycles per second. So here T is equal to 1 by F means one complete cycle is having a time period of T, which is equal to 1 by F. And here we are having the maximum point of positive side and here negative side. So if you are observing a sinusoidal waveform, in that sinusoidal waveform, you are having one positive half cycle and one negative half cycle. By combining those two half cycles, you will get a one full cycle. In the 50 Hz means 50 cycles per second. This type of cycles are completing in 1 second of 50 cycles. 50 cycles in 1 second means 50 Hz frequency. So, from this sinusoidal waveform, we will get our EMF equation means average rate of flux linkages is equal to phi maximum by 1 by 4F. What is this 1 by 4F? Means for the maximum flux position, the time period is 1 by 4F. In what way you are getting this one? T is equal to 1 by F. What happens for a half cycle? T is equal to 1 by 2F. What happens for a quarter cycle? 1 by 4F. So, from this you will get 4F phi maximum. What are the units? Here you are having Webers for flux. 1 by 4F is time period, that is seconds. Weber per seconds, or according to Faraday's laws of electromagnetic induction, the rate of change of flux linkages is nothing but a voltage or induced EMF. So, for that you are having voltage. So, Weber per second or volts. This is average rate of flux linkages, that is 4F phi maximum. After that, when you are dealing with a sinusoidal waveform, the form factor is equal to RMS value by average value. RMS value by average value. So, here you are having average rate of flux linkages. So, here we are having form factor is equal to RMS value by average value definition. And what is the value of form factor for a sinusoidal waveform? 1.11. RMS value. We are always using RMS value. So, from previous equation, what is RMS value is equal to 1.11 into average value. So, here 1.11 into 4F phi maximum volts units. Okay. So, this will become 4.44 F phi maximum volts per turn. It is the value of per turn. Actually, you are having N1 turns on primary side, N2 turns on secondary side. So, here the N1 turns and N2 turns are having different induced EMFs. So, E1 will become 4.44 F phi maximum into N1 turns. Here you are having per turn voltage. Automatically, if you are multiplying with N1, you will get N1 turns E1 induced EMF units volts. And E2 is equal to 4.44 F phi maximum N2 volts. These are the two induced EMF equations. This is simple derivation. Actually, this derivation came from Faraday's laws of electromagnetic induction, rate of change of flux linkages. Simple point. So, from that point, you are getting E1 and E2 equations in the form of 4.44 F pi maximum N1 and 4.44 F pi maximum N2. Simple difference is here, if it is E1, this is N1, if it is E2, this is N2. So, phi maximum is flux, maximum flux. Phi maximum can also be written as B maximum into A. So, where B maximum means flux density, the flux per unit area, also defined as flux density. Weber per meter square is the units. So, phi maximum is equal to B maximum into A. So, in some materials, they are giving that 4.44 F B maximum into A into N1 like that. So, anything you can write phi maximum or B maximum into A. This is the EMF equation of a transformer. After the EMF equation, you must know about the transformation ratio. What is the transformation ratio? From primary side to secondary side, you are having one particular point, that is the transformation ratio. By using this transformation ratio, you can transform the voltage and induced EMF from primary side to secondary side. That is nothing but a multiplication factor. For analog meters, you are observing some multiplication factors. From this point to that point, you are getting multiplication factors. In the same manner, you are having a transformation ratio. From where you are getting transformation ratio? By the transformer, induced EMFs E2 is by E1 is equal to 4.44 F B maximum A N2 divided by 4.44 F B maximum A N1. So, this will become N2 by N1 is equal to some constant K. The constant K is called as transformation ratio. In what way the transformation ratio is useful? At the place of equivalent circuit, it is very useful. By using this transformation ratio, you will transform the voltage from one point to another point. You will transform the resistance value, inductance value, total impedance value, like that. Only by using the transformation ratio, you can transform those values. Before going to equivalent circuit, we must go through two topics, that is a transformer on no load and a transformer on load. So, first one is a transformer on no load. If you observe one thing, from beginning the diagram is here. This diagram is very much helpful for every type of explanation in the transformer. Basic diagram is this only, and we are changing some small values in that circuit diagram. You will get your required circuit. So, suppose if it is a transformer on no load condition, we will get the transformer on no load. Like that. You are not having load on the secondary side. So, there is no secondary current flowing. So, whenever the circuit is closed, then only the current flows through that winding. So, here you are giving supply. So, you will have one doubt that I1, is there any I1 in the primary winding? Yes, because if you are giving supply to this winding and the current is flowing through this winding to maintain some flux at this part of the core. So already we discussed about the core part. Core is laminated to reduce the eddy current losses. So here the N1 turns and the current is flowing and the flux is forming. After that, whenever you are not connecting a load on the secondary side, there is no secondary current flowing in that winding. Unless until you are connecting load, the current is not flowing. Whenever you are connecting load, then automatically the secondary current also exists. So here transformer on no load means here we are having one simple phasor diagram which indicates this is a simple transformer on no load phasor diagram. So here we are having voltage and E1, E2, IW, IMU, I0 and theta. What are those values? So here the voltage, which is supply voltage, and E1 and E2 are primary and secondary induced EMFs, and IW, which is also called as working component of current, and I mu, this is magnetizing component. So working component and magnetizing component. Here you must observe one triangle from this phasor diagram, that is this is a triangle from this phasor diagram. If you naming it as A, B, C triangle, what is the cos theta of that triangle? So cos theta is equal to AC by BC. Then you will get cos theta is equal to IW by I0, where IW is equal to I0 cos theta. So here this IW will become I0 cos theta, and automatically this will become I0 sin theta. So this one and this one are equal, so I mu is equal to I0 sin theta. So this is the equation. I0 is equal to root of IW square plus I mu square from this phasor diagram. So you will get the no load current from working component and magnetizing component. So based on this formula, you are having some solved problems in your textbooks according to the syllabus. So here I am discussing about the topics, and after that I will discuss about the problems, how to solve those problems. Now the transformer on loaded condition. So then you are connecting load here. When the circuit is closed with that load, then automatically there is a secondary current existing. So whenever the circuit is closing, the current is flowing through that secondary winding. So here one important point is there. If you are dealing with the load, if it is an electrical load, you must consider the resistive load or non-inductive load and inductive load, capacitive load. Actually, basic loads are non-inductive, inductive and capacitive only. But in practical condition, the loads are combination of these three loads. Suppose what happens to your previous phasor diagram means, when it is a non-inductive load, resistance means the voltage and current are in phase. Voltage and current are in phase. Okay. After that, inductive load. What happens to your inductive load means the voltage and current are like this. This is voltage and this is current. So current is lagging with 90 degrees to voltage if it is a pure inductive load. If it is a pure capacitive load, the current is 90 degrees leading to voltage like this. The current is 90 degrees leading to voltage. But in practical case, the load is combination of these three loads. You don't know whether it is a resistive load or a non-inductive load or inductive load or capacitive load. In what way you are getting the load type means by observing the next stage, that is equivalent circuit. At that point, we are discussing about the resistance, reactance, impedance, transformation. Already we discussed about the transformation ratio. By using that transformation ratio, we will transform the values from one side to another side. So by using that transformation ratio.